I will now pass the word to Jérôme Statz, who is currently the SEABAT project coordinator. So Jérôme holds a PhD degree in electrical engineering from the University of Leuven in Belgium, as well as a Master of Science degree in energy engineering. Jérôme is an author of multiple patents, journals, and conference articles. And his professional interests are power electronics, renewable energy sources, and grid-coupled converters. In 2018, he joined Flanders Make as a research engineer, and in 2021 became Core Lab manager of the Motions Core Lab. Flanders Make is the research center for the manufacturing industry in the Flanders, and within Motions Core Lab there are about 40 people working over 25 long-term research projects. One of those research projects is the SEABAT project, which Jérôme is coordinating himself. So welcome again, Jérôme, and the floor is yours.
Thank you very much, Tommaso. Thank you for the nice introduction. Welcome, everybody. Thank you for attending this session. I'll gladly introduce to you our project, the SEABAT project, and our solutions to having large batteries for waterborne transport. Next slide, please. So to sketch how I will be tackling today, first give you a bit of context about the project and also show you how our approach is, how we are tackling these challenges that were laid out clearly by Peter, and then show you a bit of the results. So the first two work packages have already been completed in SEABAT, and they were primarily about the market analysis. So I try to summarize the main conclusions there so that you can see which vessels we target and how we go about. And then, as you will find out throughout the presentation, our main innovation is a hybrid battery. So I'll gladly give you a status update on that topic as well. So let's dive in. First, a bit of context. SEABAT stands for Solutions for Large Batteries for Waterborne Transport. Very simple name given the name of the call, but a very big challenge. Hence, we will be tackling that challenge over the course of 4 years. We started this year, as did the Current Direct project, with a budget of almost 10 million euros and 15 partners tackling the entire value chain. Flanders Make is the coordinator, and other major partners are ABBE from Belgium as well, Car Electronic, who's an expert in making batteries, but primarily for the automotive sector, and Ikerlan, a large research center in Spain. And as mentioned, our main objective is a full electric maritime hybrid battery concept. Hybrid battery meaning combining different cell types into one battery, because we believe that can be a solution, part of many solutions to figure out this challenge. And the goal with developing that is, of course, as was requested in the call and as Peter clearly laid out, to reduce the cost, not the cost of purchase, but the total cost of ownership by up to 50%. So that includes purchasing the battery, but also using the battery and, of course, the end of life or the start of its second life or third life. Within this project, we try to aim for a validated hybrid battery solution. We will bring, in reality, a 300 kilowatt hour battery, and we will prove virtually through hardware in the loop tests that our solution will work upwards of 1 megawatt hour. But we will also lay out a roadmap for type approval and a strategy for standardization to maximize the potential for uptake in the industry. So how will we do that? First, of course, we need to understand the problem that we're dealing with. We are analyzing the market for waterborne transport. We're in our first two work packages, we have looked at how the battery market has been evolving and will be evolving, made some predictions on where it is going, and tried to analyze very clearly what the requirements are and distill some KPIs, but also focus our research and determine which use cases we will focus the hybrid battery on, where they have the biggest potential to have a quick uptake after the project ends. So having that in the back of our minds, we are now developing a modular full electric hybrid battery topology, combining different cell types as mentioned before, primarily targeting a high power battery and a high energy battery combined in one. With the idea that this improves the cost, it improves also the flexibility and the scalability. So by changing the amount of high power cells and high energy cells, it can be applied in different situations, should be suitable for fast charging and so on. When we understand how this battery should work, we will build it and we will prove that it actually does work, and we will validate it for 1 megawatt hour and beyond. And of course, we want to do this as applicable as possible. So we want to go back to our initial analysis and indicate how different hybrid batteries could work in different vessel types. So our full electric maritime hybrid battery concept, what is required to make that work? Well, first we need a system architecture. We need some kind of a schematic laying out how this would work. It's not about designing the perfect battery, it's about designing a concept which is suitable for a variety of situations. And for that, you need a clear architecture, you need a clear layout. Part of that is a modular system, modularly combining high energy and high power subsystems, battery cells. The modular aspect is key because it allows you to combine and reconfigure your battery concept and create a physical battery for different varieties, for different situations. You take the same modules every time and you build a new battery for the specific use case that you're targeting. For that, we need power electronics. We need novel converter concepts, and I will introduce you to them further down in the presentation. The power electronics allow you to make these modular battery packs and to combine the high energy and the high power subsystems. And who says power electronics must understand that the flexible battery management system is essential as well. The battery management system allows you to integrate your battery, to control your battery, to understand what is going on. And if we want our concept to be scalable and sizable, the control should be scalable and sizable as well. So it needs to be flexible. And of course, our concept needs to be integrated and validated. And that should all contribute to a lower cost. What should also contribute to a lower cost is to prove the reduction of the production process in an industrial pilot. So within SEABAT, we will build these modules upwards towards 300 kilowatt hour system and prove that the production process is also cheaper. And of course, the CapEx, OpEx, and end-of-life costs should be improved with respect to the state of practice today. So within our project, we have the entire value chain involved to achieve these objectives. So we have Flanders Make, ABEE, Arkelam, and Mondragon University as a partner to design and develop power electronics, energy storage systems, and the controllers required to make them work. We have the Fraunhofer, two groups to design and develop reliable, cost-effective components and to perform a safety assessment. We have IMACAR to design and produce actual battery packs. We have Sintef and SEA to test the power systems. We have the end users on board. We have Damen, Fincantieri, Vart, and Surmar. Surmar bringing together a lot of end users just by the organization themselves. We have research and technology transfer by Politecnico di Torino. We have RINA as a technology qualification society, and we have a specialized firm, Uni Research, for project management, dissemination, and exploitation. So within the consortium of SEABAT, we actually have a lot of partners on board with a lot of different knowledge, and we believe we have captured almost the entire value chain. But we're not on our own, neither do we want to be, so we have a stakeholder group as well, stakeholders who are very closely linked to the project, who will support the uptake and will get first looks at the results, but also with whom we can interact to make sure that our results are what they need to be. So our stakeholder group is also a critical component in the value chain and in the consortium. Next slide, please. All right, so what have we been up to so far? In the market analysis, we started with, well, just looking at where we are today. So next slide, please. And it appears, as Peter mentioned, that actually Europe, when it comes to batteries in ships, is doing quite well. In 2018, Norway and France were the top 2 leading countries with regards to number of battery integrated ships. So that's quite okay. And recently, you have seen that the Mediterranean countries are starting to catch up as well and investing quite a lot. And we're actually leading the world still today. So we have a very good starting point. So if you see that there are a lot of countries in Europe where this battery technology is already present, we've had a look at where they are present. Well, actually, the Maritime Battery Forum did, and we could use those results. So next slide, please. And you see that today, ferries, offshore vessels, and passenger vessels have been the most involved units in the installation of battery systems on board. So that's also a very good starting point for SEABAT to see where our battery could have an impact today if we were to install it today, if the solution were present today. And based on this information, next slide, please, we made a forecast on how many battery systems and in which volume should be produced. And actually, this is quite a complex figure, but you see on the left side of the figure, the period from 2020 to 2025, first the number of energy storage systems to be installed, what we expect, and the volume of megawatt hours. And each bar shows the low capacity, 100 to 1,000 kilowatt hours. The middle one shows 1,000 to 3,000 kilowatt hours, and the upper one shows above 3,000 kilowatt hours, so more than 3 megawatt hours. And then from 2020 to 2025, 2025 to 2030, and 2030 to 2035, you see an increase primarily in the middle category, both in number of installed units as in volume. And actually, the 1 to 3 megawatt hour range will have predicted, of course, the same volume as the high capacity or the high energy content ships. So the 1 megawatt hour range, which was set forward by the European Commission in its call, and to which both Current Direct and SEABAT are targeting, is actually a very good category to invest on. The number of energy storage systems in the smaller ranges is also increasing, and in the upper ranges as well, but slower due to the non-availability of technology. So given this range where we are, we started looking at which specific vessels there's actually a need for battery technology. Next slide, please. So our partners went about and analyzed 34 vessels which have been electrified today or for which the plans are available, and analyzed them in depth. Because of course, when we are developing a new battery system, we want it to be as targeted as possible. So this analysis was there to focus our research, of course, not to limit our research. We started analyzing these vessels and noticed two things. First of all, in a lot of vessels, there are different cycles for the battery to operate in. Typically, you have a very often recurring cycle, which requires some energy, but not the full potential of the battery. And then there are some exceptional cases, such as bad weather conditions or emergency situations, where the load on the battery is much higher, that we refer to as a secondary cycle. And when this primary cycle and this secondary cycle are completely different, there is a potential for a hybrid battery to be a solution, because the requirements for both cycles can be quite different. So that would be a starting point to install a hybrid battery. Another analysis we did was C-rate optimization, was to consider the power versus energy content that is required in a certain application. So while application 1 may need a very high power battery with a very low energy content, and application 2 may need a very high energy content with a low power requirement, it's not necessarily that this technology is available today. And by combining power and energy into one, or different power and energy cell types into one battery type, you could directly aim or design for the optimal combination of power and energy as is required in your application. So it's also an interesting way to figure out how the hybrid battery would be suited, or where the hybrid battery would be a very good candidate. So these vessels were analyzed, and then from these analyses, we figured out the use cases for which we should aim to focus our research. And the results are that a roll-on, roll-off ferry, an urban ferry, a harbor tug, and a water bus are actually quite interesting applications. And the figure on the right bottom shows the load cycle, typical operational profile of a roll-on, roll-off ferry. And this is a very season-dependent operational profile. It has a summer profile, which is the primary 90% of the year. It's the profile when there is no ice, and this ferry makes 37 crossings per day. So it goes back and forth quite a lot, charges in the meantime, battery is not loaded at all. Whilst during winter, which is only 30 days per year, there is ice, and the ferry makes only 3 crossings per day. But it does that on a different route, which requires significantly more energy. So the annual energy throughout for the baseline battery in the cycles of 80% depth of discharge is 1,000 cycles almost. And there are 90 cycles. There are 90 cycles where we have this huge depth of discharge, but then 12,000 cycles a year where you only need 8% depth of discharge, so only this summer profile. And it's a completely different range of operating the battery, and you see that actually quite a lot in marine vessels. So these are interesting cases when considering the sizing, the scaling, and the design of the battery. So this is currently where we're at. And then we move into the hybrid battery, which actually should be a solution for that. But in order to discuss what a hybrid battery should be, it's critical to first understand what the baseline is. And the baseline for us is a regular battery, in this case, coupled to the grid of the ship through a DC-DC converter. And typically, you have a lot of cells already in modules, in series, more modules in series, and then a bunch of these series branches in parallel. And it's basically the same cell times 1,000 times 10,000, and then you have your battery, typically a lot oversized. So how do we go about when we add 2 different cell types? When we have a high energy part, but we want to add a high power part, for example? Well, a potential solution that we're investigating right now is to have a module level converter. So you take one of these modules with a bunch of cells in series, and you add a converter, a DC-DC converter, to these cells. Comes one module, and you group all these modules in series and in parallel, and you combine 2 branches, a high energy part and a high power part. Use the same converter potentially, but with different cell types, and you can combine different modules with each other. And by changing the amount of high energy and high power cells, by changing the amount of series branches and the amount of parallel branches, and by changing the percentage of high energy cells versus high power cells, you can target this towards your application. So this is one of the solutions that we are currently investigating. Another potential configuration is to use a special type of DC-DC converter called a partial power converter. And the partial power converter actually only actively processes part of the power that is being transferred between one side of the converter and the other side of the converter through magnetic coupling in the power electronics. So this has a bunch more complicated power electronics and control. And actually, the principle of the partial power converter is quite novel, let alone this being applied in a marine industry. So this is another scenario that we are currently investigating. And then the last topology that we are considering is, again, completely different. There, in the high energy part, we do not consider a converter as is typically known from the power electronics, but we switch each individual cell in the battery, which of course creates a completely new and very complex control problem, which of course we need to tackle. But it also eliminates the need for a DC-DC converter in your high energy part. However, for the high power part, it makes less sense to switch these individual cells due to the requirements. So for the high power part, we decided to keep it more traditional and couple all the different cells through one DC-DC converter. And these are the three topologies that we are currently investigating. And the idea is that by the end of this year, we will have determined which of these hybrid topologies is best suited to tackle the needs of the use cases that we identified earlier and which I showed in the slides earlier, so that we can focus our research on developing one converter, making the architecture there, and then going for building this, validating this, and bringing this as close to the market as possible. Voila. So that gave you a bit of insight in what Vlaanders and its partners are doing in the SEABAT project. Please have a look at our website where the deliverables are. The ones from Work Package 1 and Work Package 2, for which I showed some of the results, are public. So you can have a look at the forecasts and the analyses that we performed on them. You can still join our stakeholder group. My colleague Cayetano is the best person to contact. And of course, you are available for questions. Thank you for your attention, and I look forward to the Q&A and the roundtable.